All right, let's work out some basic problems to give you a better handle on how to approach equilibrium calculations. First of all, let's do a bit of a qualitative look at equilibrium. Let's take a simple reaction, say, for pen to work. Just say carbon monoxide plus oxygen. Everything's gas phase. Goes to produce to CO2 gas phase. So assume this is at equilibrium. So our equilibrium expression would be concentration of CO2 squared over concentration of CO squared times concentration of oxygen to the first power, of course. So at equilibrium, I just want to look briefly at what happens to this reaction if we disturb these equilibrium conditions. For example, if we were to add carbon monoxide. If we add carbon monoxide, we're adding a reactant. We're adding a reactant, then we're actually increasing this value here. So we're actually disturbing this reaction. It will no longer be at equilibrium, and it needs to shift back to equilibrium. To do that, it's going to have to lose carbon monoxide, form more CO2 to get our reaction quotient, Q, back to K. Remember, Q and K are calculated the same way as Q is the reaction quotient, which is really the ratio of products over reactants at a given set of conditions. The equilibrium constant K is whenever Q reaches equilibrium, then those two are equal. So in this case, what this means is if we add carbon monoxide, the reaction is going to have to shift to the right to try to reestablish equilibrium. If you lose carbon monoxide, you actually lose more oxygen too and gain more carbon dioxide, so you can reestablish this equilibrium constant. Same thing if we were to add oxygen, we'd have the same thing. If we were to, on the other hand, add carbon dioxide, now we're adding a product. Now our reaction quotient will be greater than K because we're adding a product, so the top part of our expression is going to be larger, so it needs to get smaller again to reestablish equilibrium. And therefore, this whole reaction now will shift to the left. By the same token, if we were to remove oxygen, for example, well, now we're removing one of our reactants. That's going to make our reaction quotient larger because we're getting rid of, I'll highlight this. We're getting rid of oxygen here, so this whole ratio now will be getting smaller. So to make it larger, I'm sorry, will be too large, excuse me. Since it's getting too large, it's going to have to shift back to the left to reestablish equilibrium. By the same token, if we were to remove carbon dioxide instead, now we're removing the product. That's going to make our reaction quotient smaller. To reestablish equilibrium, the process will have to shift back to the right and form more of our products to reestablish equilibrium. Again, this is a qualitative way of looking at what's happening in the equilibrium process. Remember that at equilibrium, the concentrations are constant, but the process is still constantly occurring. We still have a forward and reverse reaction that occurs, but we don't see a net change in concentrations because everything is well, I hate to say static. Concentrations are constant, but the reactions are still occurring. So if we disturb this equilibrium, then the process will have to try to reestablish the equilibrium conditions with our new concentrations. All right, so let's look at a few calculations. Suppose, for example, let's say find, sorry, it's supposed to be 2 plus lead ion concentrations and the, let's say, iodine ion concentrations for at equilibrium for lead to iodide. and we're told that the K, or in this case it's called the KSP, just to clarify, is, there was a number down, let's just assume it's about 2.0 times 10 minus 5. Well, a couple things you need to know. KSP, as I discussed, this is called solubility product. So this is telling you it's a specific type of reaction. And so in this case, what this is telling us is we have lead iodide, or lead 2 iodide, I should say. That's a solid. So solubility product means we're actually putting this in solution to make a solution. So we're adding water to this basically, to make an aqueous solution, I should say. And we'll be forming lead ions that are aqueous, plus iodine ions, also aqueous. And so we want to figure out what is going on with this expression. What is our what our equilibrium concentrations of the ions want to be. So if we go through the ice relationship, again, I'm starting with this because it makes the math a little bit simpler and easier. It's easier to show you how to do some simple calculations, and you'll get to a couple where we have quadratics, and I'll show you a couple of tricks to try to help you bypass some of the math, make it a little bit easier in some cases. So at equilibrium, this means we have at least enough of our lead iodide to saturate the solution. So this is in excess, and we often just are lazy and abbreviate excess. Initially, we have no lead, no iodide. So our changing conditions, again here, it really doesn't, it's kind of meaningless saying change in concentration of lead iodide, but for lead, we'll form X moles per liter of lead ions, and we'll form twice that many moles per liter of the iodide ions because of the coefficients of our balanced equation. And so at equilibrium, again, this is meaningless here. It's in excess and it's a solid, so it's out of phase. So we have X and 2X, so this is what makes the math a little bit easier. So our equilibrium expression for KSP is going to be, of course, lead concentration times iodine concentration, or iodide concentration squared, because there's a 2 coefficient, over 1. We do not include, again, the solid in our equilibrium expression. Since we have aqueous components, solid liquid phases are not considered because basically in that phase the lead iodide concentration is constant. And so, therefore, this equals X times 2X whole quantity squared, which is equal to our constant, which is 2.0 to the minus 5. And of course, this gives us 4x cubed equals 2.0 times 10 to the minus 5. And again, I'll point out that when doing equilibrium, the equilibrium constant is considered unitless. I don't think that's quite valid, but that's just what's done by convention. Because we have, in our expression up here, we have lead to the first power, it's molarity to the first power. Here we have molarity to the second power. So technically it should be molarity cubed, but the units are ignored and they appear later when we need them. So anyway, 4x cubed, go back and check your algebra. Just do this yourself. We solve for this relationship. We'll get 0.037. And I should point out, well, no, cube root, this will be correct. When taking square roots, you do get a plus and minus root. Remember that when you do the square root. So sometimes the negative root is actually going to be the correct value depending on how you set up your x's. So just be careful to keep track of your signs. And so we're not done here. Once we figure out x down here, we've got to plug it in to our equilibrium concentrations to find our lead and iodide concentrations. You know, the main thing is here, of course, in this case, the iodide concentration will be 2x. So this means that X concentration will be 0.037 molar. And, I'm sorry, X, what am I thinking about? the lead concentration, sorry about that. And the iodide concentration, again, equals 2x, 0.074 molar, and we're good. It's always good to double check, put these numbers back into our equilibrium expression. I would put these back in here, and we should still get something very close to 2.0 times 10 to the minus 5. I'm just going to double check that to see what it gets us. So anyway, what we should have, sorry, is 0.037 times 0.074 squared. That gives us 0.0002. Something's not right. Okay. I'll leave this in the video because I made error. I apparently typed in the wrong value to my roots. I actually typed in oops, wrong pen. Erase this. I'll erase this. Alright, so here's what we should have had if I'd done this correctly. This value should be 0.017 molar. This means our lead concentration should be 0.017 molar, and our iodide should be twice that, 0.034 molar. And I should plug this back into my equilibrium expression, so I should have 0.017, should be decimal there, times 0.034 squared. And this should give us our equilibrium constant. So it's a good way to double check that we haven't made any careless mistakes. And that gives us, this case works out exactly 2.0 times 10 to the minus 5. You can be off by a little bit, especially with problems like this where the way I wrote it down is 2 sig figs, it'll be off by a little bit. But that should give you a feel for how to do some basic calculations and how to double check yourself. Again, I just plugged this value in over here, this value in over here, and we still should get our rate constant over here if everything works out correctly. So, all right, so let's do one a little bit more complicated where we have to figure out let's say we have to use quadratic equation. Let's do a couple of these where we have to find the hydronium concentration at equilibrium. Let's say HF goes to form hydronium ions. And say the equilibrium constant here is say 4 times 10 to the minus 5 is somewhere in that range. Sometimes you'll see on Blackboard too that a K subscript A for this. This indicates this is an acid. We'll discuss acids and bases later, but it's still just a different equilibrium constant. Again, the subscripts often give us more information, Ka versus Kb versus Ksp versus Kw. It tells us more about what that reaction is. I don't care to memorize those for right now. If I give you KSP, you're not sure, I'll explain what that is. We don't have enough practice with that to get a good handle on it, so I don't want that to confuse you. It really is extra information for you, though. So let's assume that initially this is, say, 0.2 molar, 0 molar, and 0 molar. So our change, in this case, it's all 1 to 1 to 1 stoichiometry, so this will be negative x X, and X. So as we lose, it's all the same concentration, same volume of solution. So as we lose concentration of hydrofluoric acid, we'll form more hydronium and fluoride ions. As far as signs go, just to point out, if we'd used a plus sign here instead, that's fine, but then these signs would have been negative. And when you get your calculations done at the end, we cannot have a negative concentration, but the calculations would have ended up giving us a negative value for X. So you have a negative of a negative. So it takes care of itself. So just a little aside to point out that the signs will take care of themselves if you're careful with the signs. So at equilibrium, 0.2 minus X, X, and X. And of course, for our equilibrium expression, now that everything's aqueous phase, we take into account the reactants and the products. So K is going to be X times X over 0.20 minus X. Of course, this equals our constant, which is 4.0 times 10 to the minus 5. This gives us X squared is 4 times 10 to the minus 5 times 0.20 minus X. Maybe you should have said, if you want to practice your algebra, set this up, get it into the quadratic equation yourself, pause the video, come back and look at it yourself and see if we hopefully got the same things. All right, so in this case, I'll go ahead and skip ahead. We get 0 equals X squared. Let me expand this for you a little bit before we move on. We should have had, so now we get X squared plus 4.0 e minus 5x minus 8.0 times 10 to the minus 6. And of course, our root is going to be minus b plus or minus, minus b, it should be there, square root of b squared minus 4ac over 2a. And so our roots Alright, so these are our two roots that we should have gotten. And now we have to decide which one of these is actually going to be a valid root. Well, the problem with this root is that it's a negative value. And if we plug this in, period will give us a negative concentration for our products, which cannot happen. We cannot have a negative concentration. So this must be our actual root, which means that we'll write it up here. So I'm running out of space down there. X is 0.0028 molar. And this also then is 0.0028 molar. And you can again plug these back into our equilibrium expression. We should plug them back in over here. At least plug X back in to make sure that that gives us the correct value. So that gives us 3.9 times 10 to the minus 5, which is really close to, since we're doing 2 sig figs, that's expected to be off by a little bit. And so that shows you how to use the quadratic equation. It's just one step at a time. Again, this is a good place to practice your algebra. Be careful with signs. It's very easy to drop signs, to forget about minus signs. I made, even this, I made some simple mistakes here already, even on the previous slide before we got to the quadratic equation. So just be careful. That's why it's always good to double check and plug your final answer for X back into your equilibrium expression and make sure you still end up getting the same constant being calculated. So just saves lots of headache. Let's do one more here just to show you. Let's say a little bit trickier problem. Some of these are similar on Blackboard. It's actually really easy if you understand it, so I want to cover this. So again, let's find the hydronium concentration. I did a little bit more than that last time, but for, let's say, HBr, this is actually what's called strong acid. We'll discuss that a little bit next week. So this forms hydronium ions also, plus bromide ions. And this K, it's also subgroup A, but again, still equilibrium constant, is on the more on the order of 4.0 times 10 to the 6th, let's say. Now look at this number versus this constant up here. This constant is very, very small, 10 to the minus 5. That indicates this reaction is actually very, very reactant favored. Most of our chemicals are going to stay on the reactant side because that's such a small value. So our equilibrium constant is small because we have more of our reactants in that expression. Versus here, we have a very large equilibrium constant, 10 to the plus 6. That means that most of our reactants are going to go forming our products. So for this calculation, it makes it pretty easy. I'll show you one of the problems we have here at the end. So let's assume that this is initially, just make it nice easy, 0.1 molar. Initially this is 0, this is 0. Of course we have, this is our initial conditions, our change, and our equilibrium conditions. Minus x, x, and x. Here we have 0.10 minus x for our grand total. We have plus x and plus x. So for our equilibrium expression, k is going to be x times x over 0.10 minus x. That equals 4.0 times 10 to the minus 6. And so we just work out our algebra. This might be a good case for you to work out your algebra and do the quadratic yourself, then come back and see where we are. And so here, I'm going to work this out now. All right, just to let you know, I made a little careless mistake here as I was discussing the constants. I actually put 4 times 10 to the minus 6 here. And you get some really weird numbers when you do that. Nothing works out right. So just be careful with that. It's easy to lose track of these negative signs. So now, you can work out your algebra yourself and go ahead and solve the quadratic. And I'll show you the basic steps here. Of course, x squared is 4.0 times 10 to the 6th times 0.10 minus x. Of course, this is, to work this out, 4.0 times 10 to the minus 5 minus 4.0 times 10 to the 6th x, which means that 0 equals x squared plus 4.0 times 10 to the 6th x minus 4.0, sorry, 10 to the plus 5, I messed that up there. 4.0 times 10 to the 5th, and solve this and you should find the roots. So again, go work this out yourself and come back here and see if we can get the same values. So our roots, if you work this out, get 0, and we also get 2.0 sorry, 4.0 times 10 to the 6th for our two roots. This is a bit of a problem because Now, in real life, in most cases, they actually do react, but it's to such a small extent we can't actually see it or can't detect it with most techniques. And in those cases, K is very, very, very small, so all the chemicals stay on the reactant side. So if we start with initial conditions, we want to shift them as far as we can in one direction or the other in many cases, and then reestablish equilibrium from that position. So hope that helps. Really the main point is to be careful, practice the KSPs and some of the simple problems using the quadratic. These cases with very, very large, very, very small equilibrium constants, don't get too stressed by that. Have any questions, let me know. I'm not going to try to give you, any of those to be really mean on the exam or anything. So I just want you to get a good handle on the basic calculations.